Okay, very exciting. Here we are, very last section of the fourth chapter on finite state machines. So really making progress. Now, one of the main goals of the fourth chapter was to talk about nondeterminism, was to introduce the idea of nondeterminism. So in this last section, we're going to return to that, going to turn to nondeterminism, and another one of the goals of chapter 4 was to think about machines other than Turing machines. So here we are in the last section. You can see that the title is Pushdown Machines. We're going to think about a different type of machines. Okay, so let's see. We'll start in by thinking about a case that we saw last time. In the last slide, we saw in the pumping lemma that the language of balanced parentheses, I called it in the last slide a to the n, b to the n, but you could have called it open paren to the n, close paren to the n. So you got to have the same number of a's as b, the same number of open parens as closed paren. The language of balanced parentheses is not a regular language that you can't recognize with a finite state machine whether parentheses are balanced. Finite state machines do not have the power to do that job. All right, so a person might say, well, what is the minimal machine? What do we have to do to a finite state machine to bring it up to the ability to recognize balanced parentheses? So what is it that you do when you want to recognize something like balanced parentheses? And the answer is you add a stack. That's you use the data structure of a stack. So that's what we're going to do. We're going to introduce a stack. So here we go. No finite state machine can recognize the language of balanced parentheses, so this machine model, there are jobs it can't do. There are jobs it can't do that Turing machines can do. What about an intermediate machine? This machine model is not powerful enough to use, for example, if you want to decide whether input string is a valid program in a modern programming languages. I mean, if you want to do C, you're going to have balanced parentheses. That's all there is to it. So the natural data structure is a stack. So what we're going to do is we're going to take a finite state machine and we're going to attach to it a physical device that acts like a pushdown stack. I imagine that everyone is familiar with stacks, but you never know. So this is the kind of stack that you see in a restaurant. You see there are dishes on the top. And I worked in a restaurant when I was in high school. And when you take new dishes out of the dishwasher, you push them on the top. And there's a spring down here. And as you push new dishes onto the top, the whole stack slides down because it's now heavier than it was before. And so you basically have this top dish is always in the same level. When you want to take a dish off, now the whole stack weighs less, so the spring pushes it up a little bit. So again, it adjusts so that you have access to that topmost dish, but you don't have access to ones that are further down, dish 7, dish 8, dish 10. You don't. In order to get them, you'd have to take off all the dishes above it. Okay, so here's the idea. Here with a stack, this particular stack is got pushed onto it, almost like two dishes. It's got pushed onto it two different things. It's got a G3 and a G2. I'm going to use G for the stack characters just to distinguish them from things on the table. Okay, so I come along and I push something onto the stack, G1. I can no longer access G3 or G2, or at least I can no longer access it without first popping G1. Then I push on G0. Now G1 is no longer accessible. Then I pop G0. Now I can get to G1, but G0 is no longer in the memory structure. Now you might have a state in your pushdown machine. You might have a state in the attached finite state machine that somehow means have just popped a G0. Fair enough. But of course, this is a finite state machine, so you can only have finitely many such things. So if you're going to keep putting new things onto the stack, at some point you'll run out of states to mean have just pushed or just popped a GI. Okay, so the question is, what can these machines do? What can these abstract devices do? And we're not going to actually, there's only one section of the chapter. We're not actually going to get into pushdown automata very much. They're important, but we're not going to get into them very much. I only want to make a quick point about them. When we looked at finite state machines, we first introduced deterministic finite state machines, and then we introduced non-deterministic finite state machines. And then the next thing we did was to show that you can do the same jobs with a non-deterministic device as you can do with a deterministic device. So the collection of non-deterministic finite state machines recognize the same languages as the collection of deterministic finite state machines. Okay, so the two purposes here for introducing stack machines, push-down automata, is first of all to look at a different model, just like we look at finite state machines, to look at a different model, to try to capture some idea of I'm programming with a stack. That's first. And then second, the sort of real deeper reason, is that it will turn out that with non-deterministic push-down automata, you can do different jobs, more jobs, than you can do with deterministic push-down automata, push-down machines. Okay. Okay, so just want to make that point and then get out of here. So what's a push-down machine? I can define a push-down machine formally. I guess I left no space between machine and has. I apologize, a little typo. So a push-down machine has a finite set of states, including a start state and a subset of accepting states. It has a non-empty input alphabet and a non-empty stack alphabet. So you see that I called the stack alphabet gamma. That's why I say things like G0, G1, D2, because it's in gamma. And there's a transition function. So the transition function you see here, the transition function takes in a current state, takes in the character it's reading on the tape, but it also takes in possibly a blank or an empty string character, an epsilon transition character. And it also has the ability to read what's on the stack. It can read the top thing off the stack. So one thing from the stack. And then what does it put out? Why, it goes to a next state, and it also is allowed to put some collection of characters. See, that's a star there, so that's a Kleene star. It's allowed to put a string of stack characters onto the stack. And you see the basic idea here is that I have a finite state machine. That's not supposed to be a tape over there. I apologize. That's two typos in one slide. That's not very good. So I have a finite state machine, and it's got some initial characters on it. You see that they are balanced parens because it will turn out that push-down automata can recognize the language of balanced parens. So you push the start button and it starts working, but it has access to a stack. This is the stack. The stack has LIFO on it just because I think it's an amusing acronym. That stands for last in, first out. And that exactly is a perfect description of what's happening here. You put that dish on the top, that's the last dish in, well, that makes it the first dish out. Now the book has the full details, and I'm only going to give a couple of quick examples because I want to get to able to describe that a push-down machine that is non-deterministic can do at least one job that a push-down machine that is deterministic cannot do. Okay. So I'm actually not really going to go through the details very much. So here I have a machine with some states and some accepting states, and the language has sigma is open paren and closed paren. You see I made them square parens just so that it's easier to read, frankly. And the tape alphabet is got G0 because the tape alphabet's called gamma, so I call the first character G0. And the tape alphabet also has this oddball character called bottom. And then the table gives the transition function delta with the instructions numbered here, just so that I can say instruction 1 or instruction 5 or instruction 10. And what you see is that there are inputs and associated outputs. So it's really giving the transition function input-output. If the machine is in state Q0 and it's reading a open paren on the input tape, and what's on the stack is a bottom, that's what you put on the stack at the very start. Then it goes to, it pulls the bottom off the stack, and it goes to Q0 and it puts onto the stack G0 followed by a bottom. So when it pulls the bottom off the stack, it's got to put the bottom back on the stack in order to maintain the bookkeeping. One more instruction number 1. If you're in state Q0 and you're reading an open paren and you see a G0 on the stack, in other words, this is not the start, then you go to state Q0 and you push G0, G0. Now, why 2 G0s? And the answer is when you read the stack, you pull that G0 off. So if you want to keep the number of G0s, you want to keep the bookkeeping, and you want to push one G0 on, while you actually have to push two G0s on, one to make up for the one that you just pulled off. Okay, so every time you read from the stack, you're going to pop something off the stack and examine it. Okay, and you're allowed to you're allowed to put on multiple things on the stack. Okay, so basically this machine keeps a tally, a running tally of the number of open parens minus the number of closed parens as the number of G0s on the stack. And G0 is again just simply the first character in the collection here, gamma. That's all. First character in the collection gamma. Okay, so I have a computation below. This is one of these things where I really don't want to get into the hairy details, which can be a little hairy, but I do want to give a person some sense of what the heck is happening. So I have what's on the tape. This is the picture that I had earlier. You start in state Q0 and you're pointing to that first open paren. What's on the stack is this bottom character right here. Okay, the bottom character right here. So now I have read that first open paren, and you find that I effectively pushed a G0 onto the stack. Now, in actuality, when the machine works, it pulls the bottom character off the stack, and I have to push G0 and the bottom character back on the stack. But the net result is I end up with a G0 there, and that's supposed to keep track of the fact that I have read the first open paren, and so there's one thing on the stack that isn't the bottom character. There's another open paren there, so I end up having pushed a second G0 onto the stack. And again, it's a two-step process. I pull this G0 off, and then when I act, I push two G0s on, so net, I end up with an extra G0. Okay, and you see what's happening here. I have two G0s. That's supposed to designate that I've gone past two open parens. Now I have a closed paren, so I'm going to pop a G0 off. Another closed paren, I'm going to pop another G0 off, and here I am back to 0. So what that effectively means is the number of open parens minus the number of closed parens is 0. There's another open paren, so I pop another G0 on. As another closed paren, I pop that G0 that I just put on and pop it off. And then this stuff is blank here, so I find myself pulling bottom off of the stack, and because I've pulled bottom off the stack, now the machine halts. When I go to read next, there's nothing on the stack to pop, so I stop. Okay, so I'm able to measure balanced parens in this way, and again, trying to avoid the details of pushdown automata more than I need to, just because I have a point, and it isn't the details of pushdown automata. It's about the difference between deterministic and non-deterministic pushdown automata. Okay, here's the language of palindromes, but these palindromes are a certain kind. They use a C as a middle character. So if I have a palindrome, for example, let's see here, I could have A, B, C, B, A. That's a palindrome that uses C as a middle character. I could have A, C, A. So always using C to mark the middle character. And this particular machine, when it sees the C, it stops pushing and starts popping. I said that right. If it sees an A, it pushes G0 onto the stack. If it sees a B, it pushes G1 onto the stack. And then, as I said, if it sees a C, it stops pushing and goes into popping mode. When it's in popping mode, if it reads a B and what's on the stack isn't a G1, it complains. If it sees an A and what's on the stack isn't a G0, again, you're going to a state that effectively means failure. Okay, so what you see is a moderately complicated machine, and again, I'm not going to go through the details of the entire machine, but the basic idea is pretty simple. When you see an A, you push a G0 on the stack. When you see a B, you push a G1 on the stack. When you see the C, you turn from pushing into popping. And if you see a B and what you're popping is not a G1, then go to a failure state. If you see an A and what you're popping is not a G0, then go to a failure state. If you get to the end without a failure state, then you're a success. Okay, and again, a small computation, a small example of a computation just to try to give some feel for what's happening here. So you see a B, so you push a G1. You see an A, so you push a G0. You see the C, so you change from pushing to popping. Now it's an A and it was a G0, so that's good. The machine doesn't declare failure. You see a B and it's a G1, so that's good. The machine doesn't declare failure. You come to the end, you go to, as always, you always pull something off the tape. When you find yourself pulling bottom off the tape, then that's it, that they hold. Okay, so this machine accepts BACAB. Okay, so now I must be going to talk about non-deterministic machines, and sure enough I am. So to get non-determinism, we have to alter the definition in two different ways. The first way is minor. When you go back to the definition of pushdown automata, there's a B there. Remember the B there? There's a B there. Well, we don't need that B anymore because a non-deterministic machine can guess when the input is done. But the important one is that we're going to change the transition function. We're now looking here at instead of single outputs, we're now looking at sets of outputs. That's all. So the usual way to change to a non-deterministic device is to say, instead of saying that we're outputting a single pair, Q, comma, some string of elements of gamma, instead we've got sets of pairs. Okay. As always with non-determinism, we can conceptualize this either that the computation evolves as a tree, and most people, when they first start thinking about non-determinism, find that to be the most sort of felicitous way to conceptualize, or is that the machine somehow guesses one of the outputs, guesses a pair, and or is given a pair by a daemon. So we're not going to worry about too much about the two in this case, because again, we're just trying to get in and get out without having found ourselves sort of too far in. Okay, so what's happening here is this machine is going to accept going to accept palindromes, but it's going to be palindromes that don't have to have that middle marker. So if you give this machine ABBA, it will somehow know when to switch from pushing to popping. How does it know that between the two B's it's got to switch? And the answer is, we're using the sort of fanciful language. It's going to guess that this is the time to switch. Said in more formal form, there is a way for the machine to act that will end with the machine accepting ABBA. If there is a way, then we say that ABBA is accepted by this machine. Likewise, ABA. And I'm just going to point out there's a distinction between these two. Here, that AB is reversed to BA, and here that's not really true. So there's really sort of two cases they have to worry about for palindromes. Okay, so how does the machine know when to change from phase 1 to phase 2? And the answer is this machine is non-deterministic. When we first talked about non-determinism with finite state machines, I tried to emphasize how a person's first reaction is to say, it doesn't make any sense, impossible, this is stupid. Okay, it's not impossible, it's not stupid. A person might say, well, from a more sober point of view, I don't see how you build a device to do that. And of course, my response was to say, well, you have these child processes and computation evolves as a tree. But I am trying to get folks used to the idea of more and more comfortable with the idea of saying the machine chooses, or the machine guesses, or the machine is given a hint about when to change, and all the machine has to do is verify that if it does change from pushing to popping, that will work. Okay, so I'm going to say guesses here because I'm trying to alternate from the one language to the other language. So how does the machine know to change from one to the other? And the answer is it guesses. So in particular, if you compare instruction 3 with instruction 7, you'll see that the machine has the same Q0, 0, G0, Q0, 0, G0. How does the machine know which of those two to do? And the answer is there is a way for it to choose between those two instructions in such a way as to accept ABBA. Because such a way exists, we define that the machine accepts the string. And again, we will find such machines very useful. At the moment, I'm only trying to make the point that this particular pushdown automata can do something that the pushdown automata, the deterministic pushdown automata, cannot do. And that is to say, accept strings that are palindromes without that middle marker. Okay, so here I have a palindrome. This is like ABBA without that middle marker. It doesn't say 0, 1, 2, 1, 0. So the machine is not somehow told now's the time to switch. Instead, the machine has to somehow, again, guess or be told by the daemon, or more formally, there exists a sequence of instructions. There exists a branch in the tree, in the computation tree. There exists a sequence of instructions that will result in the machine accepting 0, 1, 1, 0. Okay, so this non-deterministic pushdown automata can recognize palindromes, can accept palindrome strings. And so the language of palindromes is accepted by this machine. Now, deterministic pushdown automata can't accept the language of palindromes because they don't know when to turn around. I mean, of course, that's informal language. But there is a pumping lemma for pushdown automata, and you can use the pumping lemma for pushdown automata that we're not going to cover. You can use that to show that the set of palindromes, the language of palindromes, is not accepted by a pushdown automata, by a deterministic pushdown automata. But a non-deterministic pushdown automata can. So we have a distinction between the two types of machines. For finite state machines, deterministic machines and non-deterministic machines did the same jobs. For pushdown machines, non-deterministic and deterministic do different jobs. The non-deterministic machines can do more jobs. Palindrome is the canonical case. Non-deterministic machines can do more jobs than deterministic machines. So there's a difference in the jobs that the two types of machines can do. And that's what I got in here to do. Okay, here's another computation. Now this is the second type of palindrome, the one where it's an odd length, so you have to pivot on the zero, on that middle zero. Okay, close. Last slide for this video and last slide for the chapter. So I want to compare the sort of collections of languages. What can the various machines do? So below, this box here contains all the languages. So this is the universe of all languages. I'm thinking of the alphabet, personally was thinking of the alphabet of bit strings, but you can think of it as the alphabet as the characters A and B, or the alphabet as a lowercase ASCII characters, whatever you like. So this box is a collection of all languages. And I've, of course, designated in some Venn diagram type way of different subsets. So area A here encloses the languages that are regular, the ones that are decided by some finite state machine, recognized by some finite state machine. And we've certainly seen a lot of regular language, that's absolutely right. B encloses, as a superset of A, because you don't have to use the stack if you don't want to, B encloses all the languages that are recognized by a deterministic pushdown automata. We've just seen a hint, not a proof, but a hint, that with non-deterministic pushdown automata, you can recognize, you can decide some languages that you cannot do with deterministic pushdown automata. And then finally D. With Turing machines, deterministic Turing machines, because we haven't seen non-deterministic Turing machines, with Turing machines you can decide even more languages. Not every language, because, for example, the language of the halting problem out here is not decidable with a Turing machine, but nonetheless more languages than you can do with pushdown automata. Because after all, you could write a program on a Turing machine that simulated a pushdown automata, so anything you can do with a pushdown automata you could do on a Turing machine. Okay, so what we see is this very nice structure of nested sets of languages. So we have a way to describe that we are doing jobs of a certain type. We are doing a job that has bounded memory, for example. That's a finite state machine. We're doing a job that has access to a stack. That's a pushdown automata. We're doing a job that can do sort of an arbitrary, anything that a mechanism, a sort of realistic mechanism can do. That's a Turing machine. an idealization of a realistic mechanism can do, that's a Turing machine. And what we get there is an awfully nice nested structure. Okay, very good. So always exciting to sort of work our way through a set of material. That's the end of the 4th chapter, and it's on to the 5th chapter. Very good.